Let's go ahead and start recording. So welcome everyone if you can make it. If not, hopefully you're watching this on YouTube. Fairly easy topic, but we're starting to get into functions now. How do we actually model functions in three-dimensional space? So this will kind of be the last like algebra, pre-calculus type based topic that we're doing in our Calc 3 before Monday when we return to in-person. We'll get to our calculus. We'll generalize some of the topics and some of the finer things that are coming up today to actual functions and learn the calculus on them. And then so next week we'll be playing around with all the different computations and different things we can measure of these types of functions with our calculus techniques. So today, excuse me, we are doing section 10.5. I think they call it 10.5A in the notes. So we're doing versus the book. The way we develop Calc 3 is a little bit differently. I think the book does lines and planes in the same section and then generalizes things. So we're going to start off with just lines, and then we're going to generalize this into one parameter functions on Monday. And then we'll jump back into section 10.5 once we want to do planes. Excuse me. So lines. So whenever we introduce some of these basic topics, I always like to get you guys to think back in terms of whatever your first geometry class was. I don't know, every high school education is a little bit different, but hopefully somewhere along your curriculum, you took like a general Euclidean geometry course. And so my first question I want to lead with is, what information defines a line? Another way we can think about this is, what is the minimal information that we need to be given that will dictate a line? And so asking these types of questions, like what information dictates this, is kind of a good question to ask whenever we introduce new topics, especially in Calc 3, because we will be using very similar, all these techniques we're using of dot products, cross products, they'll come up in countless number of situations. And you kind of got to like understand, well, am I doing a flux integral? Am I doing a surface integral? Are we minimizing a function? So always ask yourself when approaching a problem, like, what is the minimal information that I need, or what information am I given, and what does that sort of dictate about how I can solve the problem? These types of questions are really good ways of starting to think, especially as you're getting into higher math and higher STEM topics, whatever field of engineering or computer science, what have you, get into. So what information defines a line? Hopefully everyone remembers from Euclidean geometry. Most of the students will answer something like 2 points. In Euclidean geometry, you learn that any 2 points will define a line, and a unique line in particular. So that's a really good answer, but we want to think about it a little bit differently, especially in terms of this course. And if you think about it in terms of pre-calc, well, how do we define a line, or what information defines a line? What types of equations do we have in Calc 1? We have point slope form, and we have slope intercept form. So what are the types of information that those equations give us? Namely, it's going to give us a point. So we always need at least one point that we're passing through, but really the information that's defining a line is a direction. So you can kind of think of it like, if I have a line, you can travel along that line. It dictates a unique direction that we're traveling. And as long as we have a specific point that we've started at or that we're going to pass through, it uniquely determines a single line. So refresher of Calc 1, as I had mentioned, well, we have two equations. We have slope intercept, which is our y equals mx plus b. and our point slope form. So y minus y1 equals m x minus x1. So we want to generalize this to a three-dimensional line. And let's pull out the pieces of information that we're given. So the direction in Calc 1 is given by this slope. So hopefully everyone understands what the point is. The point is always pretty clear. Your point here, of course, is y1, x1, or x1, y1, excuse me. And slope-intercept is actually the same as point-slope form. It's just that we're using the specific point as our y-intercept, so 0b. So a point in 3 dimensions has 3 coordinates. Let's call it x1, y1, and z1. Well, so if we have x1, y1, and z1, how do we generalize our direction? What's hidden in Calc 1 in our m's is that, well, it's a relative. It is a ratio between the change of our directions. It's the relative change of our y's relative to our change in x. And we can do this in 2 dimensions or with 2 variables because we only have a ratio. We can take a ratio of 2 different things. And so what we would need to do in Calc 3, well, we would need the relative change in x, the relative change in y, and the relative change in z. And so how do we create a direction in Calc 3? Well, we can't actually create a direction as a ratio. It would be some sort of triple ratio that we would have to keep track of, which we could do, but the tool we'd have to use would be the same regardless of whether we're counting as a ratio or just a general direction. And this is going to be given as a vector. And specifically, to kind of reuse the word, it's going to be the directional vector, which I'll just write as v and give it coordinates v1, v2, and v3. So as soon as we have some starting point in space, and this holds in general spaces in higher dimensions as well, 4 dimensions, 5, as soon as you have a point and as soon as you have a direction that you're pointing in, you can walk along from that point in that specific direction as many units forward as you want or as many units backward as you want, and that's going to dictate a line. Now our problem is how do we write the equations? And we have some dimensionality things that we need to think about. So I was mentioning on previous lectures of how we want to start to think about how equations in space count as restrictions. And we want to think about the dimension of the objects that we're working with. And so a line is a one-dimensional object. So let's go ahead and write this down. Dimensions. Which, remember, we also think of as free variables or free parameters. Versus our codimension. Codimension, just think of as the remaining dimensions that we don't occupy. So if we are in 3-dimensional space and I have a line. Well, the line is still a one-dimensional object. It means it's going to occupy one dimension. Whereas the number of dimensions left is going to be 2. So for lines, our codimension is going to be 2, whereas our dimension is going to be 1. So how can we use this information a little more abstract as it's given to maybe whittle down what type of information and how are we going to dictate the equations that define this type of object? So we have a directional vector, and what we're going to have to do is we cannot write it as one given equation. This is our problem with going from a 2-dimensional space or 2 variables into 3. Because in 2 variables, I can write one equation that relates those 2 variables that will give us a line. If we want to write a set of equations, we're going to need 2 equations to restrict down our dimensions from 3 down to a 1-dimensional object. So we actually need 2 sets of equations to write down the equation of a line. Or if we want to write it as a free variable type equation, we can write it as one set of equation or one equation, but we're going to have to parameterize it. So whenever you want to think of free variables, think of the free variables that we're using in our parameterizations. So hopefully in Calc 2, everyone understood parameterizations pretty well. You got into some of the basics. You probably should have parameterized lines. And you should have parameterized more general curves. You also should have done polar coordinates, which is a type of parameterizations. Functions in polar coordinates can be thought of as a type of parameterization. So what is a parameterization? We are essentially just modeling how the X and Y coordinates change in time. At least this is what you did in Calc 2. In Calc 3, what do we need? We need equations for all of the variables. And so if we have a straight line, let's assume at first that we are walking at constant speed. So we're not speeding up or slowing down as we walk along the line. Then the change in X and the change in Y and the change in Z, relatively speaking, should all change at the same ratio, or excuse me, the same relative ratio to each other. So what are we going to have? We're going to have some starting value. Our X value is going to start at some value. Likewise, our Y and Z values are going to start at some value. And then with parameterizations, what we want to think of as, let's draw a picture here. If we have a line, we're at some point, and actually since we are in 3 variables, let's go ahead and do this in 3 dimensions. And so let's say we have some point, and maybe we're coming up and out. And if we're at this point and we are walking in a specific direction at a specific rate, let's say that's our projection here on the XY plane. Then, well, as you can kind of see, as I drew this projection on the XY plane, well, it forms a line. And if I project a line in 3 dimensions, either on the YZ plane, or if we project this line on the XZ plane, it will again form lines, meaning that the relative rates of change are going to change constantly as time ticks away. So our equations are going to be X naught plus AT, Y naught plus BT, and Z naught plus CT. This is at least with a constant speed parameterization. What does this mean? That means with every tick of time, our X coordinate is changing A units, Y coordinate changing B units, and Z coordinate changing C units. So this, well, you might be saying, well, didn't we only need one equation for 3 dimensions? And actually, this is essentially one equation that's hidden here. So, right, our information that dictates a line is a point and a directional vector. So this is what we would call our parametric equations. But parametric equations really are essentially the same thing as what we're calling in this class vector equations. So our point that we start at, let's go ahead and write down our information, x naught, y naught, z naught. And now our direction that we are traveling in is going to have coordinates a, b, and c. So we could call this point p naught, or we can call our direction v. So p naught, oftentimes we will put a vector on it. So this is something that we'll see throughout this semester, is that points and vectors are in many ways the same thing. So if you think back to our lecture on vectors, oftentimes what we call whatever point we're at in space, so let's say we're at this point on the line, we can think of that point, or we can attach a vector starting from the origin pointing to that point. So this is called our positional vector. It is the vector that points and ends directly at the point we're at. And so our vector equation for a line is going to be given as, and I'm going to write it as a function now of time, we often write it like this. So we are creating a function. Our independent parameter is time. And then our output, our dependent parameter, is our point where we are at in space, our positional vector. So f of t is common. And actually, so this is our first example of a type of function that we're going to call vector valued functions. So I wrote it as f. Sometimes, and actually oftentimes throughout this course, we'll use the letter r. And p naught, sometimes you could put it as r naught, whatever initial point you're at. Directional vectors, we commonly use v, u, sometimes w will show up there. And of course, as we saw when we learned vectors, vectors can be multiplied by scalars. So t is a scalar, it's just some real number. And so you can think as t is 0, we are starting at some point, r naught called. And then as t increases at, say, time t equals 1, we have moved away from r naught and we've added, so we've walked an additional unit length in the direction of v, or one length of v in that direction. And as t continues to move, so let's say here's our p naught, our v points in this direction. So at 1 unit of time, we've walked one length of v starting from p, and then 2 units of time, we've walked one more. And so every unit of time that ticks, we are walking 1 unit in that direction. And then we also allow time to be negative. So if we go backwards in time, it would parameterize the full line from minus infinity to infinity. So just an abstract mathematical note that R of t is our first example of a vector valued function. So we like to study functions. All of calculus was a study of functions, a study of rates of change, and how do we measure the rates of change of functions. And now we've got to do all this in 3 dimensions. So it's going to be important, at least for me, I think, when introducing calculus, especially in Calc 3, with all these different dimensions that are going to be thrown around this semester, it's kind of important to think about what directions we're moving back and forth from. So this we would notate as f. So if it were f as a function, we write it as this. So from R to R3. So our independent variable is one dimension, our output is a vector in 3 dimensions. Or you could use the letter R, of course, is a function from 1 dimension into 3 dimensions. And we'll talk more about this maybe on Monday as well. Now, when our independent variable, since we only have one independent variable, a lot of the calculus is actually very similar to how it is just with Calc 1, how our derivatives are going to work out. We just got to be careful of what's going on with the extra coordinates, with the extra dimensions in there, our output variable. So this is our one equation that defines a line. And again, the number of free variables, the number of independent variables, our free parameters, dictates how many dimensions this object is. So it's just a one-dimensional object in space. And so if we wanted to do this codimension concept, how many equations, if I were just to try to write equations relating x, y, and z, as we commonly do in Calc 1, well, how would I get a one-dimensional object? We can't. Well, we can't with one equation. We need at least 2 equations. And so this brings us to our what we call our symmetric equations. So our symmetric equations, if we take a look at our parametrization up here, what do we want to do with our symmetric equations? We want to just dictate the points on this line without having this extra free parameter. In some sense, you kind of think of, well, there's almost like 4 variables going on here. We have our x, y, and z coordinates, and then plus this one extra free parameter. Sometimes it's a little extra information to keep track of. If we just want to relate x, y, and z, how do we do that? Well, let's go ahead and start with these parametric equations. Let's drop the dependency just for the arguments, just for the really for a visual sake. So if we have our x, our y, and our z, if we solve each equation for time, well, what we're going to get are a system of equations that we can then set equal to each other. Since all of these equations, or at least the right side over here, are all equal to time, then I can set each of those equal to each other. So what do we get when we set those equal to each other? We get our 2 sets of equations. It's actually 3, but it's the third equation is redundant based off of the information that we're given. So there's really 2 unique equations here. So we'll have x minus x naught over a is equal to y minus y naught over b is one equation. And then our third equation, z minus z naught over c. And so let me just rewrite that. These are our symmetric equations. So those are the 3 different ways we can write a line. Personally, I will use most often the vector equations. Easiest to write down, it's just one equation. It's kind of a nice and concise way of keeping track of our information. Vectors are really nice for that. It's just oftentimes, especially in like computer science and programming, whenever you create a vector or a list type object, sometimes it's just used for keeping track of a list of information, which in many ways can be thought of as what we're doing here geometrically. There's just some extra geometric information. We're keeping track of our change in x, our change in y, and our change in z in our directional vector. So examples. So find, let's say, the vector and symmetric equations for the line through 1, 2, minus 1, and minus 2, 1, minus 2. So vector equations, what do we need? We need a point and we need a direction. So we have our point. We could choose either starting point we want, and then how do we find our direction? Well, if we want to find our directional vector, we simply take the difference between the 2 points. So if we use, say, PQ as our directional vector, this means we want to walk from P to Q. We take the difference of the ending minus the start, so Q minus P. So we'll get minus 3, minus 1, and minus 1. And so our line is going to be given by R of t is equal to, and still we can choose any starting point. Since we have our directional vector as PQ, I'm going to choose P as our starting point. And then plus the directional vector times t. As a check, what's going to happen when t is equal to 1? So we've cooked this system of equations up so that if I start at p and walk 1 unit in this direction, or at least add on this vector, 1 unit of time times this vector, we should end up at q. So when t is 1, we'll have minus 2x. We will have 1 on the y coordinate, and then we will have minus 2 on the z coordinate. So it starts at P, ends at Q. This is the line we're looking for. So from here, if you want, you can always use the formula to directly write the symmetric equations. If we want to move into our vector equations, we can always combine these if we'd like and write them within each coordinate. So what I mean is we have x starting at 1 minus 3t. So that's our x linear equation. Our y starts at 2 minus t. And then z is minus 1 minus t. So another good set of vector equations. We can then if you want to write these individually, write your parametric equations for any of those. And then our symmetric equations, we're going to have x minus 1 over negative 3. And then we're going to have that equal to y minus 2 over negative 1, which is equal to z plus 1 over negative 1. And so these will be our symmetric equations. If you want to finagle some of these minus signs in the denominator, you can do that as well. So we can write this as 1 minus x over 3 is equal to 2 minus y is equal to negative 1 minus z, just to get rid of those minus signs in the denominator. And of course, the minus ones aren't really needed. Now, if we wanted to restrict ourselves to a finite segment, This just means we want to restrict our t values. So if we restrict the domain, we'll restrict ourselves to a finite segment. So if we wanted to restrict ourselves between the finite segment between p and q, we would use the same equations, but just restrict t between 0 and 1. So we found the specific t values. We already kind of talked about the specific t values. At t equals 0, we start at p, cooked it up so that at t equals 1, we end at q. And so we would just restrict our time between that domain. Okay, so we want to talk about parallel, skew, and intersecting. So two lines are parallel if the directional vectors are the same. So that one's pretty simple. Just like in pre-calc, two lines are going to be parallel if the slopes are the same. So in Calc 3, two lines are going to be parallel if the directional vectors are going to be the same. So however you deduce the directional vectors, if the information is given to you as symmetric equations, you'll have to deduce the directional vectors as the relative rates of change. Nicely enough, usually if the information is given as a vector equation or as parametric equations, it's usually fairly easy to pick off what the directional vector is for a given equation of a line. So same directional vector, they are at least parallel. How would you tell if two lines are going to be the same? So one of the problems we actually run into with lines and parametric equations in general is that there are a lot of different parametrizations of a given shape, of a given curve. So how do you tell if they're the same? You want to be able to, one, determine if it's linear. If the two lines, if you do know that they are both lines, how do you determine if they're the same? They need the same directional vector, but the starting values can be different. So you got to be careful about that. What you would have to do is to check to see if they both have a common point. So if you can find one point that's in common on both lines and they both have the same directional vector, then it's going to be the same. Conversely, if you know that they have different points, but the same directional vector, different lines, but parallel. We might see an example of that here in a second, once we get to more of the examples in the notes. So let's take a look at an example. We'll talk about skew and intersecting here in a second. Let's do one example, and maybe those topics will come up here. Let's give L1 is going to be given as R of t is equal to 1 minus t, 2 plus t, 2t minus 1. And I guess we could call this R1. Let's call this L2 is R2. And our equations are 2 plus t, 5 plus 3t, and t. Actually, I'm realizing I just misspoke a little bit. Directional vectors do not necessarily need to be the same. Let's take a look at what's going on with this example. They need to point in the same direction, I guess we should say. So here's our equations of lines. We've got R1 and R2. So we can rewrite these a little bit. R1, our point is going to be 1, 2, minus 1. And then the directional vector is going to be minus 1, 1, and 2. R2 starts at 2, 5, and then no starting z coordinate, or starts at the 0 for our starting z coordinate. And our directional vector is 1, 3, 1 times t. So these two vectors are not going to be parallel. So let's go back and make a correction ourselves. So directional vectors are not necessarily the same. If they are the same, they will be parallel. Are scalar multiples of each other. So they're going to be pointing in the same direction. However, because there are different parameterizations, our step size could be different. So we could be walking, could even be speeding up. We'll work with that on Monday. But the step size we're walking for any given unit time interval could be different. So, or we could walk in the opposite direction potentially. So just scalar multiples of the same directional vector. So our question with this example is, well, are they parallel? We would want, let's call this one V1 and V2. So if we want to check parallel, the first question we want to ask is V1 equal to some scalar multiple, let's say C times V2. Hopefully everyone can see, no, what would this mean? This would mean that our coordinates, so minus 1 has to equal C. It would mean that 1 has to equal 3 times C, and that 2 has to equal C as well. So we get a contradiction that C has to be 3 different numbers. So no solution means that they are not parallel. We want to ask, are they skew or are they intersecting? So we've got a little bit of a problem. Let me go ahead and rewrite the equations here. We've got R1 and we've got R2. So skew and intersecting, this is something that can happen now in 3 dimensions, where I can have lines that are non-parallel, but they also don't intersect. So that's essentially what skew means. So skew, non-parallel, non-intersecting. Because we can have one line and then some other line sitting above it, and lines that just look like this, and they're traveling in different directions, never touch each other. So that does bring up a question, though, is, well, we know they're not parallel. do they intersect? Do they intersect? And so how are we going to tell if they intersect? Our problem is that the t-values could be different. So let's maybe draw a picture here and take a look at what might happen. If we have intersecting lines, that intersect at a point, the purely geometric information tells us, well, they intersect. I should be able to find this point. In 2D, with just two equations of lines, it's pretty easy to do. We can set both equations equal to their point slope form or slope intercept form, solve for y, and then set the two equations equal to each other. This is going to be another thing that we have to be careful of that happens with vector valued functions. Namely, that two functions can intersect at the same time, or they can intersect, but they might intersect at different times. Think of it like playing sports or something like that. If you throw a ball to someone, if someone's running, they're on a specific path or a trajectory. We can model that with a system of equations. And then you throw a ball directly at them or to them to where they're going to go. You want that ball to hit them at that same point in time. However, if that person runs, you could throw the ball, and that ball, the path of the ball, might intersect the path of the person. But if you threw it incorrectly, you might throw it behind them. So you threw it to a point where they were running. So the paths cross, but that person wasn't there at the same time. So we've got to be careful with the types of questions we're asking and how do we go about solving them. So for example, in our lines, even though both of these lines might pass through a common point, if my starting value, by the way we've parameterized our green line, is here, whereas the starting value for the magenta line was at this point of intersection, well, even though the lines have geometrically a common point, the times that they are at that point are going to be different. So what do we have to do? We want to be able to set the equations equal to each other. However, we've got to actually use a different independent parameter for both of our lines. So what we're going to do, let's actually go ahead and write down our other set of equations. Let's write down our parametric equations. Because what do we want? At the point of intersection, we want to lose track of this notion of the parametrization. We want to lose track of this notion of what time were we at that point. We want to know specifically what are the coordinates of the point. We need to know our x, y, and z information. So for R1, we have x is equal to 1 minus 1. Or sorry, x is equal to, 1 minus t. Our y is equal to 2 plus t. And our z is equal to minus 1 plus 2t. Our other equations, let's go ahead and change this second parameter to an s, is our common other parameter that we're going to use. So we also are going to know that x is 2 plus s, y is 5 plus 3s, and then z is just equal to s. And so what do we want? We want the x, y's, and z's to be equal to each other. So we simply set those equal to each other. We'll get 1 minus t is 2 plus s. We'll get 2 plus t is 5 plus 3s. And our z coordinate -1 plus 2t is equal to s. So we've got a system of 3 equations. We only have 2 unknowns now, our t and s. So we check to see if this is solvable. If it is solvable, we will find the common point of intersection. If it's not solvable, it means they're skew. Let's go ahead and label our equations. Equation 1, equation 2, and equation 3. Equation 3 looks like it's easiest to start with since we have already solved for s. S is -1 plus 2t. We can go ahead and plug that into either of the other equations. And then what we want to do is check the last remaining equation. So since equation 1 only has one coefficient of our s variable, let's go ahead and substitute it in there. So I usually like to write my steps. This will be important for linear algebra. You'll do a lot of stuff like this. So I usually stick 3 into equation 1. And so what are we going to get? We'll have 1 minus t is equal to 2 plus -1 plus 2t. And then now we can solve for our time. 1 minus t is 1 plus t, 2t. And then we subtract, we'll get 3t equals 0, t equals 0. And so now our question is, will this hold? Because if t is equal to 0, we can plug that back into here. And that's going to tell us that s is equal to -1. And then maybe we'll take these two into equation 2. And what's that going to tell us? That'll tell us 2 is equal to 5 plus 3 times -1. And it looks like we'll get 2 equals 2. So I simply took our t value, plugged it back into our equation 3, once we solved it using equations 1 and 3 to find our s, and then verified both of those values in equation 2. And since it works out, we are good. So what is our specific point of intersection? We found the respective times that each line crosses the point. We found our t and our s values. That means if we plug those t and s values back into our equations, actually, let's go ahead and do it up here. So if our t is 0, this is going to be 1, 2, and -1 of where we intersect. And then we'll plug in our t and z in -1 into our s, or sorry, our -1 just into our s equations, and we get 1, 2, and -1 again. So our common point is at 1, 2, -1. Okay, so let's do one more example before we wrap this up. And let's talk about the shortest distance between a point and a line. So very common problem that we're going to see in Calc 3, where we have some sort of geometric object, a line, a surface, a plane, and we have a point outside of that, and we want to know what's the shortest distance. If we are standing outside from a region, we want to know how far away am I from the region? What's the shortest distance I could walk to get to that region? So let's see. Do we have, oh, we do not have an example. Let's make one up. Let's maybe use our line as 1, 0, -1 plus, say, 2 - 1, 1 t, and our point, let's just call it p. And let's say 3, 3, 1. So there's a couple different ways we could do this. The Calc 1 way to do it would be to use the distance formula. There, Calc 1. We want to minimize something, the shortest distance. We want to minimize distance. So we have x, y, and z. We can write parametric equations of our lines. We have a specific point, 3, 3, 1. So we could use the distance formula for the change in x squared plus change in y squared plus change in z squared, and then minimize that with respect to the time variable. So you guys are honor students. I'll leave it to you guys. Check that. Try that on your own. But now we've developed some stronger tools now in Calc 3. And we've talked about projections and components. So this is another reason why we were looking at this notion of relative frames and relative components of a vector. If we have a line, as we've mentioned, a line composed of a point and some directional vector, let's call this here our point. Let's call this point Q on our line. And if I have some point out in space, let's call this our point P. The shortest distance from a point to a line or from a point to any sort of geometric object should be orthogonal. How do we find the orthogonal component specifically? Well, what we could do is, if I know a point P, we know we have some point on the line Q. We have some starting point on the line. We could find the vector PQ. That's going to point in the direction from Q to P or P to Q, whichever one we want, whichever direction we want. But that may not be the shortest distance. If we walk from P and then hit Q, while we will be on the line, it's not necessarily the shortest distance to get there. How do we find the shortest distance, or how do we find the path we should travel to find the shortest distance? Well, we would want to start from P and walk orthogonal to the line. In other words, we could take this directional vector PQ or QP if you want to flip it, and then project or find the orthogonal component relative to our directional vector. So we can start with PQ. And I guess for the sake of doing this, PQ, since we're pointing in this direction, let's go ahead and change the direction of that arrow. Start with PQ and then find, and I'm going to change that. Let's call this U just for simplicity of writing. Find the orthogonal projection onto V of U. So let's go ahead and do that real quick. So if we have our P as 3, 3, 1 and our Q, let's go ahead and take Q as 1, 0, minus 1. These numbers may not work out since I've kind of made up this example. Our PQ is going to be, we want to do, P to Q. So let's do Q minus P. We've got -2, -3, and -2. And so let's also call this our U. And then now, how do we find our orthogonal projection? Our V is 2 minus 1, 1. And our component, let's go ahead and find our vector projection onto V of U is going to be our dot product U dot V over norm V squared in the direction of V. Let's go ahead and find our components of this formula. So our U dot V is going to be -2 times 2 plus -3 times 1 will give us 3, -2 times 1 will give us -2. So we got -4, -1, -3. And then our norm V, let's keep it as norm squared. Norm squared is always easier to compute. This is going to be 2 squared plus -1 squared plus 1 squared. So it's going to give us 6. So if you've got all that written down, let's go ahead and I'll need a new page here. Our projection onto V of U is U dot V, which was -3. Norm V squared was 6. And then V itself was 2 minus 1, 1. How do we find our orthogonal component? We take V, or excuse me, we take U, and then we subtract off the component in the direction of V. So our U is -2, -3, -2. And then we are subtracting off what we just found, which will be -1/2 times 2 minus 1, 1. Numbers aren't too bad. A little bit of fractions here. So -2, -3, -2 plus 1 minus 1/2, 1/2. And so what are we going to get? -1, -3 minus 1/2 is -3.5, so -7/2. And then -2 plus 1/2 is -3/2. So let's go back to our picture. What did we just found? What did we just find? We had PQ. We projected it on here. So we're pointing this direction. Because we took PQ, we subtracted off this component. And so this is our orthogonal component of U onto V. So the length of that is going to give us our distance. So our distance equals the length or the magnitude of the orthogonal component. So that's going to be square root of 1 plus, maybe now the numbers aren't going to be so great. So what are we going to get here? Square root of 58 plus 4 is 62 over 4. Any easy ways to simplify that numerator? I don't think so. So 62 is what, 2 and 31? 31's prime? Yeah, so root 62 over 2. Now, with a lot of these computations in Calc 3, let's go back and check ourselves. As you've seen already, I will make plenty of mistakes, especially arithmetic mistakes happen all the time. So video's we're about done. So let's go ahead and how do we check ourselves? Other things that the problem might ask is, well, what point do we hit? This is one check we can perform. I know we have point Q on the line, but if I walk from P in this direction of the orthogonal component, we should be on the line. Namely, P plus our orthogonal component so let's write this. This is our check. And be careful with this. There are some homework problems along the lines of, or that will ask stuff like this. At least there was last semester. Always be careful what direction you're walking in. If we had found QP and then projected on, if you start at P and walk in the opposite direction, you're never going to hit the line. So always be careful of the direction that you're making these. So we did do PQ from P to Q, and then we subtracted off V. So if we start at P and walk in the direction of that orthogonal component, we should be on the line. So let's check that real quick. So our P was 331 plus our orthogonal component, -1, -7 halves, -3 halves. What are we going to get? We get 2 and -1 half and -1 half. And so is this point on our line? If we go back to our equation, looks like we made some mistakes. Because this implies that, oh no, maybe we didn't. Hold up. So here's our line. So our starting point on our line was 1, 0, -1. So if our x coordinate needs to be 2, what's that for our time? So I'm not really writing this out formally, but you can now check. We would need to check what time we hit this point. So again, you can get a system of equations of x, y, and z of what our time should be through. What our time should be. Let's just talk it out real quick. So since our directional vector is 2, we need t to be 1/2. Sounds promising. So if our t is 1/2, we will get 2 in our x coordinate. If our t is 1/2, we will get -1/2 in our y coordinate. If our t is 1/2, we will get -1/2 in our z coordinate. Boom, we got it. Good, no mistakes here. So it looks like we got it right. All right, so that is it for lecture. Hope you guys have a happy Friday. If you're flying in today, hopefully the airports are all right. Looks like the snow might have eased up a little bit, but it looks like it can also keep coming down. So I will see you guys in person on Monday. Look forward to meeting everyone. And we're in our new classroom. So in the honors, what is it, the dorm, the building you guys are all in. So look forward to seeing everyone, and I will see you later.
Thank you.